How are you today?
I'm doing great.
Is this your first interview or did you have it before?
Yeah, it's not my first one. I've been tried a few times.
So let's focus on the maximum of 55 minutes. So I can have about 5 minutes to build your feedback. So are you going to program with Python?
No, I'm going to use Java.
Paste the question here at the beginning of the file. Please share your screen.
This is a example.
Yes.
So essentially, first row 1, 3, 5, 7. Last row is this one, 10. Okay, and the last one is this. All right. The second question. So the first one is search for target 3. So we say, okay, it's over here. This is a match. So yes, it's true. And want to search for target 13. We know 13 is over here. And it's between 11 and 16. So we know it's a false. Okay. And okay, the question sounds very simple. Okay, so search. Let me see the property. The property is that each value in the row is shorted, and then the last value of previous row is smaller than the first value of current row. Essentially, if we consider the row, we look at the rows all together. Essentially, this is all essentially, even though it's a 2D array, but essentially we look at that. Essentially it is it's a linear structure, and the whole linear structure is shorted. So essentially, the intuition is that to answer whether a value is in the matrix is going to be the same as answer whether a value is present in the equivalent sorted list, essentially, right? So sorted array or sorted array. So that's essentially that we can directly if we can map that, essentially the two questions or problems are canonical, and canonical essentially we can there are many ways so to do that. So search on the single list, the sorted list or array. We know how to do that. The fast one could be a binary search, right? Or we're doing right. That's the fastest one. Give you a log-n search time, and however, convert from the original problem to the second problem is going to be order n. So essentially, it's going to be taking the simple approach. Is saying that it's going to take m plus log n. Essentially, is linear time to search that. So that's the first idea, right? So okay. Any question?
No, that is clear.
Okay. So the question will be, shall we employ a better algorithm to do that? Because we know I feel we may be able to get it down to using a log n or log something like that. We should be able to achieve that, right? So essentially, let me see.
Sure.
Ideally, okay. So if we consider this, I think that in my brain something is happening over here like this. So if we can do because now 1, 10, 23 is also sorted, right? So then I think we can basically conceptually we can do a binary search on 1, 10, 23 and figure out which row we should conduct a search, right? And then from that row we can do a binary search, which is going to be a log n, right? And right. So that will be log n plus log n. So essentially, almost linear, right? So essentially that's sounds like a way to go. So now we need to figure out some details on that. Do you feel okay?
Yeah, I agree.
Okay, so now assume that this is we probably don't care about the details of that. Let me drop this one. So essentially, what do you want? So essentially, let's define the API we want to have. So now it's going to be search, right? And then it's going to be a 2D array, right? Data, right?
Right.
Right. So given that, I think so this is going to be a okay. So now it's m by n. Did he? I think okay over here, right? Assuming m is the okay. That sounds good. But now we know the first thing we want to search is actually among a sorted array of size m. So now let's say we wait a minute. Yes, hold on. Do I need to so essentially I need to do two search for the row. That's right. Let's see. I feel that I may not be able to get it in right. Okay, so how do we do that? And okay, this is probably not the best, but let's say the temp is going to be older m. So we populate this this temp populate this essentially populate temp from the from data's first column. Okay, so let me focus on the search logic. Sure. Okay. Okay, now let's focus on that. So suppose now temp is the array of size m. Now I want to search. So how do we do that? So I want to search 3. And so in this case, it should be falling into a column 0. The index should be, the row index should be 0. So and let's see. So in this case, I would say I'm going to search this one, the arrays of temp, right? I'm going to search for the target value, which is given. Yeah, I missed the one. What's the and target? So I'm going to search this target. So now, binary search of that. So it's very likely the one with the target we search happen to be the first index. In this case, this one it should be 1, 10, and 23, right? So this is array we're going to search for. If we search for 1, it's going to be, so essentially it's very possible that the row give us a hit, right? So essentially the row is actually exactly the row index we should go for, right? However, if the value is sitting on first row, it's going to return the second index and the minus. So essentially, okay, I know. So now, if that less than 0, because this is Java thing. If that in this case, 3 is a miss, right? So essentially, it's going to return, the row return is going to negative value. So I think the formula to get an actual location for the actual insert according to Java is going to be minus row minus 1 is going to be the place for you to insert. You want to pretend you want to insert. So and therefore this is going to tell us this going to give us 1, right? And this is actually I'm going to 1 is not 1. So essentially I would say equals to this one. So now so in this case this part is too fast. Sorry, there are some details about the Java API thing, but I think this formula is correct. So this is dealing with a case that if 3 is not among 1, 10, 20, 23, I say this formula is going to reset a row to be index 1, to the index 0. If we search for 16, and this formula is going to give us index 1. If we search for 10, and this thing will not fall in, and the row is giving us index 1. So now we have, okay, so now we are going to apply binary search to an array of data array given the index we just acquired, say on the search target. In this case, because it's going to say, hey, it's fun or not, right? So it's going to be, okay, this is the place we return. If this place return is greater, is less than 0, and that means it's not fun. So essentially we'll say greater than 0. So if it's greater or less than 0, that means it's we found it. Otherwise, it's not, right?
Mm-hmm.
So that's final search. Okay, so that's I think this algorithm should work.
Okay.
Are you okay? If okay, then I will spell out the complexity for space and time, and then see if we can go do better.
I will ask some questions, but for now, let's discuss the time complexity for this one.
Okay, cool. So over here, let's see time complexity. Time over here is going to be order n population, right? For time, order n. Search for row index, and it's going to be order log n, and over here is going to be order log n. So it's going to be order of m plus log m.
Why it's order of m, the first one?
Because you still need to populate this one, right? We need to populate this temp size m. So remember this m, we need to find out, get 1, 10, 23 populated in this fashion.
I see. Okay.
Right. So I think that's the part that I'm not so happy about, because see, we can get rid of that term. So this m over here, right? So this is population.
Mm-hmm.
Right.
And is it actually populating? It's just creating an array, but it's not filling the array.
Creating array. So here's the population. Yes. So okay. So that's the part I say that if we have time, we'll do it. So essentially, we'll say I equals to 0 and I less than m. So now we'll say I was just skipping for now. Just fill in the detail. It's going to be data I 0. Right.
Okay. And yeah, it's linear. So let's try to see if we can make it logarithmic.
Okay. Yep. And yes. Let's see. Yeah. So this, because of this term is linear. How do I search this one?
You might need to write your own binary search instead of using this the predefined one, because the predefined one. Wait a second. Yeah.
Yeah. So and let me see. And IJ. Yeah. So and okay. So I got your point. So we can do that. So essentially, this is a 1, right? So let's see. Search for target I and J. So now I'm going to search the target. The Yep, I think that's good enough. So so the calling into this API is going to be I is going to be 0, J is going to be M star N minus 1, and so so the I, okay, let's see, INT, I think this is gonna, that's the outside, how outside is calling into this one. So another way to search doing this, that, so then I do binary search, IJ are both inclusive. So essentially what happens is that we are mapping a 2-dimensional array into a linear structure, and linear structure is I is actually n x plus is that right? Hold on. So this is the n. I is the x is the row index. So x times n plus y. So essentially the formula to translating a xy, translating a position xy to a linear is this formula. Sorry. Let's see, somewhere we'll use that. Is that clear? Sorry. Hello?
Yes.
Okay, good. So now this one's essentially reduced to oh, I see. Now I see ij. Okay, that's the other way around. So from ij to xy is different. So now here's the thing. So the other way around. So ij is a linear index, and then we need to find out the actual position. Okay, hold on. Sorry, this is I think this is the main part. It's called, yes, it's called POS or coordinate. It's fine. Given a linear index, we translate to a 2D index, right?
Mm-hmm.
So that's the main part, right? So essentially, I want to return array of IDX. Essentially, this is what? This is divide by n, right? And IDS, is it right? Mod, yes,
Yeah.
mod n. That's correct. That's correct. That's correct, right? So essentially, for each position, I will have one. We have one. This is star. Let's make it really obvious, right? So that's basically start. So start in is a linear. Linear position. Now internally we map it into a 2D position by using this one, by using this API. Then we can actually perform the task. Oh, sorry. Okay, now here's that. So I say we want to do our own binary search, and the way to do that, let me see how to do it. So I star and end. Okay, good. So now I think this is correct. We need 2 pointers. We need this one. So immediately we'll say or calculate middle point equals to 1. So this is the midpoint, right? So we will say, do I calculate midpoint over here? Maybe later. So I will say the whole thing will stop while, and wait a minute. So star and end are both inclusive, right? So that means that if star less or equal than end, those are valid. So I want the other way around. So when this happens, we will exit that. So now, and okay. How do we, hold on. I see. If I get a loop, I cannot still cannot answer the question. That means I cannot find it. I return false. Otherwise, when I am in the process, right? So now I have a mid. When I have a mid, and I should be able to transition the mid into a position, into a P, which is position of mid, position of M. So now, once I have that, I will be able to say, hey, if the happy path of data P then, so now What? So now we basically start. So now what happens if, okay, yes. So if the current position is bigger than the target. So let me see. So now I have P. Position is bigger. Sorry, let me see. I have a value. I'm scratching on this. So target. So the target is to the left. Target is to the left. So basically I will shrink right. So then that means my R need to be redefined. R needs to be defined to be M minus 1. Otherwise, L needs to be, we shrink left, is going to be M plus 1. Right, let me see. So we start in, we'll do this thing, and we terminate when starting as doesn't make sense anymore. It doesn't constitute a valid interval divided by starting n, then asset. Otherwise, calculate middle point, linear middle point, transition to 2D middle point. On 2D middle point, we compare the value with target. This is a hit. Otherwise, we recurse. Not recurse. Binary reduce the scope. I think we're good.
So let's see. So can you run one of the examples on the above? Let's say example 2.
So going to run this guy.
Yes.
Over here.
Yes.
So this guy, right, into this, and the entry point is going to be the way to enter is going to be search the data, right, and the star is going to be 0, right, and 3 times 4, 12 minus 11, right, and target is 13, right. Okay, now, so let's see. Right. So starting n is going to be 1 and 13, right? So 1 and 13. 1 and 11. 1 and 11, right? So and this one, sorry.
I think
That one.
Okay.
Yeah.
Okay.
So this is correct. So while this is true, we continue to lock. When now it's violated, when you jump up. So 11, 1 less than 11, great. So when this happens, it's going to be, so the midpoint is 6, right? So midpoint.
Wait, why is the start 1? You said the search is 0, 11, 13. Yeah. Okay.
So it's going to be, what? 5? Right? So 0, so let me put down something help us here. This is going to be what? 4, right? And this is going to be what? 8? Right? So now 5 is going to be this guy, 11. So 11 is over. So this is, so now this is going to be 11, right? So 11 doesn't equal to what? 13, right? However, 11 is less.
Wait a second. How? I don't think that it's 11, right? P means position of M. Can you? So the position of N.
Oh, right, 5. Okay. 0, 1, 2, 3, 4, 5. Right. Position 5. Position 5. Right.
No, in the position function that you wrote.
Right. Position function.
So 5 divided by 3 is 1.
5. So 5 come in. 5 divided by n. N is 4, right?
And is 4, right?
Right. So n is 4, and n is 4, right? So essentially,
I
it's,
think. Mm-hmm.
it's going to be 5 divided by 4 and 5 mod 4, right?
Both of them n, or one of them should be m?
This one should be no, should be n.
So the matrix is an m by n matrix.
M by n, right? M by n.
Right.
M by n, right?
Right.
So now the thing is you're looking for 5, right? So the position of 5 is over here, right? 0, 1, 2, 3, 4.
I agree. The thing is that the position function that you wrote, I think the first one is trying to find the row, the second one is trying to find a column. So
Yeah.
I think it should be IDX divided by m and modularized m, or modularized n.
Let me see. Yes, I think so. That's right, right? So basically,
Right.
what is m? M is, in this case, 3, right?
Yes.
Yes, that's correct. Is that right?
In 5 divided, at least for this example, the answer is the same, right? It would be
Right. So it's be 1.
1, 1, which is the 11.
I think the still it should be n. I think it should be n. Sorry.
So both of them, you are saying that both of them should be n?
Right. Both of them should be n. I think so.
So it doesn't matter if you have a matrix square or non-square. Let's do it with n and see what will happen. Then we can come back and discuss it.
Yeah. Okay. Right. So let's see. So this one comes out to be what? To be 1, 1, right?
Mm-hmm.
And 1, 1 is since 11, we know, right? And then we know 11 is less than this one. 11 less than 13,
Mm-hmm.
right? So
Right.
we know L will be m plus 1. That means L becomes what? M is what? M is 6.
Mm-hmm.
L becomes 6, right? So now L becomes 6 over here. So now, so this is the 6th position. Position 6. So now, what is that? L position 6 over here, right? And
But you don't call the search function, so it.
Yeah, but this is
Yes, right.
loop, right?
Okay,
Because,
yes.
Yeah, so iterations are much better than
Mm-hmm.
we can avoid, right? So now
Okay.
come back to this one. Now 6 plus this one minus 2 is going to be 17 divided by 2. 17 divided by 2 is going to be 8, right?
Mm-hmm.
M equal to 8. So that's getting into this one. So how about this one? So A and A. 8 and A is going to be Q and 0. So position A, this guy.
Mm-hmm.
Position, so the 2, 0. So now we know position 2, 0 is 23rd, right? So 23rd, so this one from here. And the 23rd is greater than 13. So that falls into the block. So now R equals to M minus 1. R over here equals to, what is the M? M we say is R equals to M minus 1. This one becomes 7.
Mm-hmm.
Right? Okay.
Right.
Now, says straw L. And this is a mistake. I'm sorry. This one. Still, the L is less than 7. Great. So now it's going to be 13, right? 13 minus 2, which is going to be 6. M is going to be 6. So what's am I right? Yes, M is going to be 6, right? So now position 6 over here is going to be 6 and 6, right? 6 divided by that is going to be 1 and the 2, right? 6 position is first row 1 is going to be this guy, right? Great. So 6 we say, and the value, this one, okay, and it's going to be value is on this one is going to be 16, and 16 is greater than 13, right? So all comes to place. Now we're saying that we are going to decrement reassign R to be m minus 1. M is going to be 6, so R is going to be 5. 5, right? So now, so now we ask, hey, is 5 less or equal to? Is that right? L is 6, right? L is 6, and R is 5. So is it correct? So this one says no, it's false, right? So you jump out. So you turn false. So it turns out what happened is that we didn't find value of 13.
Okay. Yeah.
Right. Okay.
Okay.
So the only confusion is about this part. I think this is correct. I think so. Sorry.
Okay. I can try to give another example, but let's see. Position. Okay, can we discuss the time complexity?
Yeah, sure. Let's see. So the color, from color's perspective, we can do another wrap, but anyways, I think it's just a matter of a small thing. Let's do that. So because I think over here we'll just do return this guy. Search of data from 0 and MN's over here. It's going to be M star M minus 1 and target. So this is a full function here. So over here, this in stack is constant time. So there's no space, no time consumption here, right? So that's part. But for this part, what do we do is iteration is not recursive. So again, those are in stack. Not is fine. Stack is fine, and so space-wise, we are not allocating any extra space. And how about time? Time, we know that this one coming, the size of this guy, we don't need this one anymore. The size of this one is order. Totally, this data of this over here is MN, order MN, right? So M star N, but we know in binary search, MN essentially, we come here, we know that this totally star and N is going to be order, size-wise, right? It's going to be the distance, the length between star and N is going to be order MN. We know that each time the algorithm is saying that each time we figure out a midpoint, and if we're lucky, we return. However, if we're not lucky, each time we're chopping the whole thing in half, right? Because we do this kind of thing. So essentially, this is standard binary search complexity, and it's going to be log this guy, right? Okay. So yeah. So and then this is going to reflect on this guy as well. This is for time. So space is actually constant. We don't work much.
Okay, sounds good. I think we can stop here, and I wrote some feedback that we can discuss.
All right.
And then I'll open the ground for you. If you have any question or if you want to discuss anything, feel free to do so. So from my note, what worked very good was that when you read the question, you were able to come up with the idea very quickly. You were able to use the feature of the question, which was the array was sorted, to come up with the solution, with the efficient solution of using binary search. And this was all good. Also, what I liked about the first approach that you took was that you tried to add comments, which was making the high-level architecture clear. I mean, definitely it wasn't the solution that we were looking for, but still the way that you were thinking about implementing it was good. Also, when you were trying to understand the problem, I noticed that you redrew one of the matrix to make it more visually it was much better to understand line 15 to 17, I mean. So it means that you try to understand the examples very well. I think these were what worked very well. The things that I can comment out that you might be able to improve is that, I mean, you were able to write the binary search at the end, and you mentioned that it's been a while that it didn't work. So I think maybe writing the actual while loop for the binary search can be written faster if you just practice and remember it better. But that's it. That's what I have to tell. But other than that, I think it went well. Are the comments clear?
Yes, that's really helpful. Thank you.